This conference will now be recorded.
Okay, so welcome everyone. Today, it's my pleasure to introduce our guest speaker, John Kitching. So Dr. John Kitching is the leader of the Atomic Device and Instrumentation Group in NIST, Physical Measurement Laboratory, and a NIST Fellow. He received his Ph.D. in Applied Physics from California Institute of Technology in 1995. He and his group pioneered the development of the microfabricated chip-scale atomic device for the use as frequency reference, magnetometer, and other sensors. He is a fellow of the American Physical Society, and he received many awards for his work, including the Department of Commerce Silver and Gold Medal, the 2015 IEEE Senior Council Technical Achievement Award, the IEEE UFFC Robbie Award, and the 2014 Rank Prize. He has published over 100 papers in reference journals, has given numerous invited and plenary talks, and he has been awarded 6 patents. So without further ado, John, the floor is yours.
Great, thank you. So let me just share my screen here. All right, can you see that? Okay, hang on just a minute. Let me, is that good? Can you see it?
Yes.
Nope, hang on a minute. I gotta change. Well, yeah, is that good now? Is it full screen?
Yes.
Perfect.
Yep.
All right, good. Well, thank you, Ahmad, for
Please everyone put the microphone on mute so John will not have any interrupt. Thank you, everyone.
Great, thanks. Yeah, so thank you, Ahmad, for the invitation, for the opportunity to tell you a little bit about this chip scale clock work that I've been involved in almost exactly 20 years now. It was actually in December of the year 2000 that we started thinking about this in collaboration with DARPA, and it's been really interesting for me to see how this whole technology has evolved over the last 20 years, and most interesting now to see how it's being used in various things. And I was quite excited to see this timing card that you've all put together with the chip scale clock in it. It's very kind of gratifying to me that someone's actually using this and that it's making an impact in the real world. Okay, so let me just start off by way of introduction. I think that most of you are probably familiar with various types of clocks. This is a slide that I use a lot to show just kind of the spectrum of different technologies. You know, the most accurate clocks now are optical clocks that are based on optical transitions in atoms. And these achieve spectacularly high precision and accuracy, approaching 10 to the minus 18. But of course, these are really advanced instruments. They're basically laboratory devices. They take up the better part of a room to make them work, and kilowatts of power. And of course, there's not even any commercial instruments really based on these. And so they're in some ways at the moment much kind of a laboratory curiosity. On the other hand, you know, on the other hand, down at the other end here, there's wristwatch quartz oscillators, which of course, you know, are very small, low power. They're very inexpensive and basically ubiquitous in our world today. And in between, there's a whole bunch of sort of technologies that kind of span this whole range from, you know, very high performance, but also large, power hungry and expensive, down to you know, the much less costly things that of course have much lower accuracy. And of course, you know, these all have a place in technology infrastructure in the real world. You know, for satellite-based navigation, you really kind of want timing at the nanosecond level. That's determined by the speed of light and the fact that you want to position something to within, say, a meter. Optical fiber telecommunication systems, you maybe want 100 nanoseconds or maybe a little better. For wireless communications, you want sort of on the microsecond level. And then for consumer electronics, you really kind of want things kind of at the millisecond level, really. So you know, every one of these type of technologies really has its place in applications. And I'll say that, you know, one of the things that's interesting as a physicist, you know, all the physics is really kind of up here at the high performance end of things, but really all the economic impact is down at the lower end here. The market for quartz oscillators is something like, I don't know, 10 or 50 times as large as all these atomic clocks combined. And so it's an interesting question to say, okay, you know, we have all these very high performance atomic instruments. How can we push them down toward the lower cost and lower power consumption and smaller size so that they could be used more widely in real world applications? So why do we bother with atomic clocks in the first place? Really this comes down to quantum mechanics. An atom, if it's just sitting in space unperturbed, is a very simple quantum system that is composed. The dynamics are pretty much defined by the nucleus and the single valence electron in the case of an alkali atom. And so that leads to very simple energy level structure. In particular, the electron can interact electrostatically with the charge of the nucleus, and the electron and the nucleus both also have magnetic moments. And so depending on the alignment of those magnetic moments, the energy of the whole system can change. And ultimately, you know, because this is such a simple quantum system, you know, what that leads to ultimately is, you know, very, very good long-term stability. And also fundamentally, it leads to SI traceability and accuracy to the extent that we can sort of realize this perfect unperturbed atomic system. And so, you know, if you look, for example, you know, this is just a simple plot showing the Allen deviation, the timing stability for one of the best quartz oscillators, the ultra-stable oscillator, compared to a 5071 atomic beam standard. And you can see that quartz oscillators do spectacularly well at short integration times, you know, below about a second or a few seconds. But if you want to time things over days or weeks, atomic standards always do better. And so that's why atomic standards have a particular use, is it really in timing things that over very long time periods. So I mentioned this sort of quantum mechanics and how this you know, gives good long-term stability. And when you kind of look at least for a microwave atomic clock, kind of what goes on here, you know, the real sort of dynamics for this microwave clock is determined by the alignment of the electron magnetic moment with the nuclear magnetic moment. And so just like with two bar magnets, if you have the north poles kind of pointing in the same direction, that has a higher energy than a configuration where the north poles are pointing in opposite directions. And just like that, in an atomic system, there are energy levels that are defined by the relative orientation of the electron and the nuclear magnetic moment. And but the key difference, of course, compared to bar magnets is that because the energy levels here are quantized, you have discrete energy levels that define a specific separation in frequency that can be used for precision timing. So how do atomic clocks work? Well, the most sort of conventional way of making an atomic clock is to essentially drive the atoms with a microwave field. And so if the atoms see some kind of an oscillating magnetic field that is part of the microwave field, then the atoms can be driven into an oscillating state where essentially the magnetic moment is changing in time. And this is very much like driving a pendulum. If you drive it at exactly the right frequency, you generate a large amplitude of motion in the pendulum, or a large magnetic moment essentially in the atoms. And that defines a resonant frequency. In the case of the pendulum, is determined by gravitational acceleration and the length of the pendulum. And in the case of atoms, is defined by this quantized energy level difference and Planck's constant. And of course, you can see here that with classical sort of mechanical oscillators, you know, this length here, and even the acceleration due to gravity can change due to various environmental perturbations, and that changes the frequency. Whereas to the extent that you can really realize this quantized energy level structure in an atomic system, this frequency is well defined and in principle doesn't depend on any major environmental factors. So, you know, atomics, the clocks that I'm going to talk about are all based on thermal vapor of alkali atoms in a vapor cell. And so typically what we do is we take atoms of cesium or rubidium and we put them in some kind of an evacuated cell, usually made out of glass. The atoms are confined that way, and then we can interrogate the atoms using microwaves or lasers or whatever we want. Now, if the atoms were just stationary things, everything would be wonderful. You could start them ticking, essentially oscillating, and then they would sit and oscillate for a long period of time. But of course, things are not that good, and the main problem is that the atoms are at room temperature, which means that they're flying around at thermal velocities of a few hundred meters per second. And what that means is if you have a cell that's, say, a centimeter in size, it only takes a few microseconds for the atoms to go across the cell and collide with a wall. And these wall collisions basically introduce strong either phase or even just relaxation effects that sort of destroy or interrupt the actual coherence of the atom. And so if you're using this to time something, of course, then you know every time the atom collides with the wall, then you get this interruption in the timing. And if you phrase this in terms of the quality factor, you know, if you have say a 10 gigahertz oscillation frequency here, you might have quality factors on the order of 10 to the 4, which is okay, but it certainly doesn't give very high performance. So there are two ways that have been developed over the years to deal with this. The first is you can basically coat the walls of the cell, the interior walls of the cell, with some kind of material that doesn't interrupt this coherence as much. And so people sometimes use wax coatings, paraffin, for example. But the more common technique is to use a buffer gas inside the cell. So if you put, for example, say a tenth of an atmosphere of nitrogen in the cell with the cesium, then the alkali atoms collide with these nitrogen gas particles, and you know the mean free path might be a micron or a few microns or something. And so the atoms essentially diffuse through the cell now. They don't fly ballistically from one side to the other. And if you arrange this gas to have a very benign effect on the atomic oscillation, the hyperfine coherence in this case, then you can get much longer coherence times for the atoms. And in fact, in cells that are a centimeter in scale, now everything's determined by the diffusion constant of the rubidium atoms or the cesium atoms, and that can be on the order of tens of milliseconds, leading to much higher quality factors. And ultimately, of course, the stability of a clock is inversely proportional to that quality factor. And so the higher the quality factor, the narrower the resonance is in frequency, and the better the stability of the clock is. So all the clocks I'm going to talk about until the very end are based on buffer gas vapor cells. So throughout the 1990s, there was a pretty substantial effort in the clock community to develop compact clocks, mainly for cell phone base stations. So this was at the time of huge growth in cell phone usage, and a lot of these clocks were developed specifically for that application. And so these were clocks that were about 100 cubic centimeters in size. They ran on somewhere between 5 and 15 watts, and they achieved stability sort of in the 10 to the minus 11 range. And the cost of these clocks was on the order of $1,000. And as I mentioned, the main application was cell phone network synchronization. As probably you know better than I, cell phone networks need to be synchronized at the microsecond level. It's usually done using GPS, but you need to have holdover clocks inside your base stations in order to maintain the timing of the station in the event that GPS is unavailable for some reason. So there was a big effort here, and again, these were the kinds of instruments that were developed at that time. So you could ask, well, why would we want to make clocks smaller than this? And I would say this was kind of the case 20 years ago, and is still largely the case now, that there are many applications, and in fact many growing applications that involve battery operated units. And you can think of GPS receivers, wireless communication devices like cell phones, or you can think of remote sensing, underwater applications. And so there's many places where you want to have very good timing, but you don't have, say, infinite power, or you also might want to have small size. And so one of the ways you can think about this is, a lithium-ion battery, for example, has an energy density of a few hundred milliwatt hours per cubic centimeter. And so if you've got a 5-watt clock, well, you can only run this thing for a few minutes on a 1cc battery before the battery's dead. But if you can reduce that down to the 50 milliwatt range, then it can run for many hours on a 1cc battery. And so now you kind of get to the point where if you could make a clock that was sort of a cubic centimeter in size and ran on 50 milliwatts of power, now you could have something that could maintain timing for extended periods, and that potentially can be a useful thing. And so this kind of defines a little bit like the size and power goals for what we might want to have in a portable frequency reference. A cubic centimeter dictated but kind of by the size of a portable device, and then 30 milliwatts having to do with basically the energy density that you have in a battery of that size. And so early on in this sort of chip scale clock research effort, there were some specific applications that were identified, and the first two here are kind of that at the time in the early 2000s. Of course, there were these sort of wars going on in Afghanistan and Iraq. And one of the big issues was that GPS receivers that are heavily used by the military are very susceptible to jamming. GPS is a very weak signal, and so it's not so hard to jam it just by blasting RF power in that range. And so there was a lot of interest in developing GPS receivers that could be insensitive or less sensitive to jamming. And it turns out that if you have a good clock inside your GPS receiver, it means that you can actually directly acquire the military PY code, which is much less sensitive to jamming. If you don't have a good clock, then you generally have to acquire the civilian code first to get the time, and then with that time, you can then acquire the military code. And so that was one of the motivations. There were others that were outlined, for example, secure communication systems where you have frequency hopping radios, spectrum radios, basically. And if you could hop quickly enough with a high enough accuracy, then you could make it more secure. And actually, since that time, maybe in the last 10 years or so, one of the really critical applications that's emerged is underwater seismic sensing. And this is for basically oil exploration. One of the ways that oil companies look for oil is to use acoustic waves that travel into the rock strata and then are reflected off the boundaries. And if you have seismic sensors on the ocean floor and you have good timing, then you can sort of measure the phase of this reflected acoustic wave, and that requires sort of millisecond level timing over months. And so that is hard to do. There's no GPS down there. Everything's got to be run on a battery. And so this is actually now the major application for chip scale clocks, at least as of a year ago. These are evolving in time, of course, is this particular thing. And yeah, so, and there have been, I think, as many of you know, there have been over 100,000 chip scale atomic clocks sold over the last 10 years or so. And so it really is sort of now a technology that can be deployed with pretty high confidence that it's going to work, and there are many applications and some growing applications that take advantage of the particular features of the technology. Maybe just some motivation on power. You say, okay, how much power consumption could I get away with here? How low could I make it? And a lot of this is determined by the basic kind of fundamental law of blackbody radiation. If I have a cell that I'm heating, and that cell has a certain dimension, and so there's a certain surface area, then I can calculate through the Stefan Boltzmann law the amount of heat that's radiated by that into some ambient environment. And so if my cell happens to be, say, 100 degrees C, and ambient is, say, 0 degrees C, I can say, okay, how much power is radiated, and it's just given by this formula here. And what you sort of end up with is that, if you want to have, a power consumption on the 10 milliwatt level, then you really need to have the size of this thing that's hot at the 1 millimeter level. If it's any larger than this, you can see that the power consumption goes up quite dramatically. So for example, if it's a centimeter in size, just to keep the thing hot, you've got to keep it up at, you might take a couple hundred milliwatts of power, and that's already kind of blown the power budget if you want to operate this thing on a battery. So another development that was important for this type of technology was all optical excitation of these atoms. So I mentioned before that sort of the most generic way of making a microwave clock is you take the atoms, you optically pump them into some hyperfine level, and then you apply a microwave field to the atoms, right? And that causes transitions between those energy levels. And by monitoring the strength of those transitions, then you can determine when your oscillator frequency corresponds to the atomic transition. And one of the problems with that, of course, is that you have to apply microwaves to the atoms. And so in at least the simplest microwave cavities, you want to have the length of the cavity, the size of the cavity, on the order of the microwave wavelength. And that typically means on the order of centimeters. And so there was work in the 1980s and 1990s to develop alternatives to this direct microwave excitation of the atoms. And one of them is shown here. This is the idea here is instead of applying the microwave to the atoms, you use the nonlinearity that's intrinsic to atomic systems. And what you do then is you take, say, an optical field, and you either amplitude or phase modulate that optical field at the hyperfine frequency of the atoms. And as you know, any nonlinear system, if you drive it with two frequencies, then you can generate an oscillation at the sum or the difference of those frequencies through the nonlinearity. And that's exactly what happens here. The atoms are nonlinear. And so if you apply now a modulated optical field, which is basically a carrier with sidebands, then either the pair of sidebands or the carrier in a sideband can produce these optical fields now, which then can excite an oscillation at the difference frequency. And if that difference frequency happens to be resonant with a transition, a microwave transition in the atoms, then you get a response essentially, which is can be observed by just looking at the amount of optical power that's transmitted through the atomic ensemble. And so what happens in this case then is you're driving the laser, you're modulating the laser current, and now as you scan this local oscillator frequency, you see a change in the transmission of the light through the atoms, and you can use that essentially to lock up your local oscillator. And so if your local oscillator starts off kind of varying in time, now you stabilize it to the atomic system and you get something that's much better. So this is another key ingredient in chip-scale atomic clocks, is this all optical excitation. And part of it is, again, this issue that you don't have to use the microwave cavity, which has some implications in terms of the size of the device, but it also has implications that it just is a lot simpler to modulate the current of a laser than it is to actually build your microwave cavity and apply the microwave to the atoms. And so I think this simplicity is one of the things that has enabled the technology to grow in a very in a fast way and actually work in the real world because it's very simple. So I mentioned laser technology. So we need to have a laser we can modulate, but one of the key aspects is we also want to have very low power consumption. So so of course we're looking at semiconductor lasers here. They're by far the simplest and lowest power laser that you can at least buy commercially. And most semiconductor lasers are edge emitting lasers, which basically means there's a gain region here and there's mirrors that are on kind of the sides, the edges of the wafer, and the light comes out parallel to the wafer plane. There was a different type of laser that was developed in the 1980s and 1990s called the vertical cavity surface emitting laser. And you can see this laser structure is different. It has a gain region, and then it has a series of mirrors that form the optical cavity that are actually oriented perpendicular to the wafer surface. And this means that the optical cavity is very small. The mirrors can be made very, very high reflecting. They're basically Bragg stacks, and so they can be made very high reflecting. And this basically means that the threshold current of these lasers can be very low. With typical edge emitting lasers, the threshold currents might be 20, 30 milliamps. these can operate with threshold currents well below 1 milliamp. And so now you can get coherent light out of this that you can use for spectroscopy of atoms with only, say, a few milliwatts of electrical power put into the device. And this has been an absolutely critical aspect of chip-scale clock technology, because without the VCSEL, it would be very difficult to generate the optical fields that are needed to make the clock work. And here's pictures of some devices. This is a package device here. You can see the little tiny VCSEL. This is actually in our lab. We buy them in die form, and then we mount them onto this is a ceramic base plate with gold traces on it, and then we wire bond to the main thing here. And so anyway, so this is really a key part of the chip scale clock technology. The other key part is the silicon micromachining. And so I mentioned that this issue with the blackbody radiation, right? And you need to have a cell that is very small in order to be able to achieve low power operation, low power heating of the cell up to the operating temperature. And so we got interested in using silicon micromachining processes. Of course, you probably are familiar with this. Silicon micromachining is kind of the mechanical analog of integrated circuits. You basically start with a silicon wafer, and then you expose a photoresist or a mask, and then instead of defining electrical structures, you actually etch material. So you define mechanical structures. And silicon micromachining has got many uses. Probably the first one was accelerometers and airbags in cars, but now, of course, every cell phone has got a silicon micromachine accelerometer and gyro in it, and they're used in digital light processors and microfluidics. So it's a big field that uses this type of silicon processing. And so we got interested in this. So now you say, okay, how am I going to make a very small and low power atomic clock, right? So this is the basic design of the clocks that I showed you that were developed in the 1990s. They're largely based on, the heart of it is this absorption rubidium cell here, which is usually made using glass blowing techniques. But another key aspect is how you produce the light to interrogate the atoms. And this has been traditionally done using a discharge lamp. You essentially put RF power, and it excites these atoms, the atoms of rubidium into their higher lying levels, and then they emit radiation as they decay back to the ground state. You need to do some filtering in order to create spectrally non-homogeneous light. And so this is kind of the design. You have this light, the lamp, you have a filter cell. The light then goes into the absorption cell, and which is itself inside a microwave cavity. And then you just monitor the transmitted power as a function of the microwave frequency, and you can see a resonance that then you can lock up your microwave oscillator to. So how do we miniaturize this? Well, the first thing we want to do is to get rid of this lamp, because this discharge lamps typically run on the order of a watt of power. And if you want to get down to the milliwatt range, that's got to go. So we already know that we have diode lasers that can operate and generate light with fairly low power consumption. And so we're going to replace this, the light source and the filter cell with a diode laser. The next thing we're going to do is get rid of this microwave cavity, because the microwave cavity, as I said, is kind of large, and it does add complexity to the system. And so what we're going to do now is, instead of applying the microwaves directly to the atoms, we're going to actually just modulate the laser current and generate this modulated light beam that will be used then to generate this coherent population trapping resonance in the atomic system. And then finally, we're going to take this absorption cell and we're going to make it really small. And this is going to reduce the amount of power that's required to heat the vapor cell up to its operating temperature. So that's kind of it. And these three elements are really the things that I would say kind of define what we would call a chip scale atomic clock. And as you'll see, this really does lead to fairly dramatic improvement in the power consumption of the device. So I mentioned vapor cells. Historically, until about 15 years ago, the way that vapor cells were made was using glass blowing techniques. And so you essentially took a glass tube. Hang on a minute, I'm going to give you pointer here? Okay, there we go. It took a little glass tube, and then you would fuse windows onto the glass tube, and then you'd have a filling tube, and you'd attach this whole thing to a vacuum manifold. You'd pump it down, and then you'd break open an ampule of rubidium or cesium, and you'd kind of distill the alkali atoms into this cell, and then finally you'd seal the cell with a torch. And you get cells that look something like this. This is a quarter here, and this is the vapor cell, and here's the filling tube with a little kind of clipped off end here. And so this, this is it works well, and cells were made for decades using this technique. But of course, they're big, and it's hard to make them small because it's a glass blowing process, and you have to make them one by one. And so the technique that our group developed in roughly 2003 is using this silicon micromachining. So essentially what we do is we start with a silicon wafer about 1 millimeter thick. We etch a hole in that silicon wafer using standard silicon micromachining. And then we somehow fill this with our alkali atoms and our buffer gas, and we bond glass onto the top and bottom surfaces to essentially seal the alkali atoms inside this evacuated hermetic enclosure. We actually, the technique that we use is a technique called anodic bonding. It's a way of bonding glass to silicon by heating it up to about 300 C, and then you apply maybe 1,000 volts across the interface, and you get a very, very nice bond. And the great thing about the bond is it doesn't involve any kind of stuff, any other stuff like glue or anything else. It's a very clean bond. It involves a little bit of oxygen during the process, but for the most part, it's a way of making very, very clean cells that don't have any contaminants inside them that can disrupt or cause changes in the frequency of the atoms. And so these are pictures of cells that we made back in 2003, roughly. This is, you can see about square millimeter in cross section, maybe 500, 600 microns across. And the other, of course, advantage of this is that you can make, because this is now an etched process, you can do everything in parallel. And so you can, in principle, make large numbers of cells using the same process sequence, reducing the cost of the cells down to a much lower value. These cost on the order of $100 to make per cell, and you can make these for less than $1 per cell. So there's a big advantage in terms of cost here. And ultimately, we're not quite there yet, but like my vision for this all along has been to sort of make these like wafers of all the different components and basically make, atomic clocks that you could sort of dice up and just sort of like you would make an integrated circuit and be able to make them very, very low cost. Hang on a minute, this is not changing. See if there we go. Okay, so there's been a few different cell methods. So the real trick is how you get the alkali atoms inside the cell, right? Because alkali atoms are very reactive. They react with oxygen and water. And so you got to keep them in some kind of a clean environment while you're doing the deposition and sealing the cell. And so one of the early techniques was just to do the kind of simplest thing you might think of, and that's to sort of break open a cesium ampule in some kind of an anaerobic chamber that has all or most of the oxygen and water pumped out, and then just kind of dip a little pipette or a pin or something into the liquid cesium and put it into the cell. This is what we call a preform here, which is basically the yellow is the silicon that has been bonded to a glass wafer shown in blue, and then the top is still open, so you can put things in it. And then you want to make sure that your buffer gas is the right buffer gas. So you take this from your anaerobic chamber, you put it in a bell jar, you'd pump all the gas out, put in your buffer gas, and then finally you'd put the lid down inside the bell jar and then bond this using anodic bonding to enclose the gas and the rubidium inside the cell. And so that's one technique that is still used, I believe, in industry today. The technique that we developed, it's a little better, I think, because it's a little cleaner, is we use a reaction of barium azide and alkali chloride. So you can buy, rubidium chloride or cesium chloride, it's just salt basically. And then barium azide is actually an explosive, but you can buy it. It's actually was, I think, used in airbag accelerometers as the thing that explodes basically. And so you can buy this in solution basically, and then you dissolve some of this salt, this rubidium chloride, and it turns out that these two chemicals, you put them in an ampule and dry it out so that you're left with no water, just a powder. And then if you heat these up to about I don't know, 200 degrees C, they react and they form nitrogen, barium chloride, and your alkali metal. And so you can do this then in a high vacuum chamber. You put these materials in here, you heat it up. Now it reacts and it produces nitrogen, which is just pumped away. And then you have a little small beam of cesium or rubidium atoms that, again, it gets deposited down to the bottom of the cell. And then once you've done that, you can backfill with a buffer gas and again do this bonding step inside the vacuum chamber to seal the cell closed, and you can kind of make whatever buffer gas you want inside there. And there have been, we actually pioneered these two techniques. We've been using this one in our laboratory for the last 20 years roughly. But there have been a number of other techniques that have been developed by other groups around the world to do something, essentially equivalent process here to figure out how to get your alkali atoms in the cell. And one kind of recent result from our group is just in the last couple of years, we've now been able to make large wafers of cells with alkali atoms. And I'm not going to go through the whole process here. Actually, the paper on this just came out yesterday. And so if you're interested, it's in Journal of Physics, Photonics, UK publication. But there's also a patent that's been filed on this. But you can see that we're able to make now wafers of these, and all of these little white spots that you see there is condensed rubidium that is inside one of these cells. What you're seeing actually is a silicon wafer with glass bonded onto the top and bottom, and you can see where the bond is not working quite well at the edges here, but most of it's bonded pretty well. And the close-up here, you can kind of see one of these vapor cells. Again, this is, I think, 2 millimeters on a side, and this little metallic-looking thing is actually rubidium metal that is condensed on the inside window of this particular vapor cell. And so this is all bonded nicely, so then you can sort of dice these up into small cells and use them. So this now is a process that now allows you to make hundreds, possibly thousands of cells using the same process sequence. And it takes about a day or two maybe to make these. And so that basically reduces the cost of the cell if you want a lot of them to basically zero. Okay, so now we turn these into clocks, and this is actually a picture of the very first physics package that we built. I remember we got it working the day before Thanksgiving in 2003. And I remember actually going into the lab on Thanksgiving morning to play around with this thing, and because it was pretty fantastic to get it all working. And you can see it's a bit of a monster. We had to, these wire bonds are kind of nuts here. You know, we would try to do the wire bond and it wouldn't work, and it'd break, and we'd use glue and stuff. And but the thing worked. And actually, this is actually on display now in the Smithsonian Air and Space Museum on the Mall in Washington, D.C. And so if you go there, maybe once it reopens after the pandemic, you can actually see this the very first device that we built on display there. That one was a little bit difficult to work with, so we sort of made some future, well, better and more reliable devices. And this was made a few months later. Again, the structure here is we have the vertical cavity surface emitting lasers sitting on the bottom. The light is emitted upwards through some optics here. And then the vapor cell is sitting here. And then finally, the photodiode is on the very top. And there are some heaters here that allow us to heat the cell. And so this device was, again, about the size of a grain of rice, 10 cubic millimeters in volume. And it ran, at least in ambient temperatures, on about 75 milliwatts of power. So how did this perform? Well, a first measurement on this, so this is the black data is actually the frequency stability that we measured on that device I just showed you. And so you can see, we were able to get sort of 10 to the minus 10 stability, and there was a substantial frequency drift that we observed in the first devices. And by making various improvements to the cell fabrication method and using a little bit different interrogation, we were able to improve this in next year down into the mid 10 to the minus 12s at say 1,000 seconds. Again, there is some drift here that's mainly due to temperature effects. We didn't work very hard on the temperature issues, but so in the end, the commercial device that was released by Symmetricom in 2011 is shown here. It's a little bit worse at short integration times because they had to make some compromises in the local oscillator chain. But you can see it also is much better at long integration times than what we did, and that's in large part because of the thermal engineering and temperature compensation of the buffer gas. So, so this is kind of the pretty standard curve that you get in terms of frequency stability from these. And just to compare these to other things, you know, if you look at the CSAC stability compared to other vapor cell clocks, you know, it's worse. And that's mainly because the cell is smaller. And because the cell is smaller, the atoms collide with the walls more often, and it has faster relaxation. And so you can see that, you know, it's about a factor of 10 or something like that worse than conventional clocks. But if you compare this CSAC to something of equivalent power, because all of these things are several watts of power, and the commercial CSAC runs on 100 milliwatts of power. So if you compare this, for example, to a low power oven-controlled quartz oscillator, you can see it like integration times of a day. This is at least 2 orders of magnitude better. And so this is really where the strength of the device is. It's in the power consumption. So this is another kind of reflection on that. This is the power consumption of various types of atomic clocks as a function of kind of the release year. So the HP 5065 was, I think, the first commercially available vapor cell clock. It was a rack-mounted device, so it was on a 19-inch rack essentially, and the physics package was about 1 liter or something in size, and that ran on about 40 watts of power. And you can see over 40 years, you know, the power consumption kind of went down to maybe 10 watts. CSAC is sitting down here at 120 milliwatts of power, and so it's a very substantial power reduction compared to any previous technology. And again, as I mentioned, really driven by the use of the laser, the use of micromachining, and the use of this all optical interrogation. So this is why, for the most part, I think for most applications, this is why it's important, is because the power consumption is low. Now you can look at the timing error of a chip scale clock. So this is basically the timing error if you synchronize it at a certain amount of time, and then you ask, well, how wrong is it after a certain amount of time? You know, just the simple timing dispersion that you get can give you sort of a microsecond a day. But of course, there are drift effects and other things. And so once you allow it to operate over, say, the spec temperature range and voltage range, you're left with a timing error that's on the order of 100 microseconds at a day. And of course, if you leave it on the shelf for a while, there is a slow drift of the clock, and so if you don't recalibrate the frequency, then that leads to increasing timing error that would require recalibration to remove. So this is kind of the number that I usually talk about is, it'll hold 100 microseconds for a day on 120 milliwatts of power. Of course, it'll do better than that if you're willing to operate it at a constant temperature and make sure do some conditioning of the power supply that you use to drive it. You can get down into the microsecond range in a day. So just a note on like the technology development process here. This was a program that was funded by DARPA starting in about 2002, and so you can kind of see the concept was really developed back in roughly 2001, and 2 or 3 years later we had MEMS vapor cells and physics packages, and then a couple of years after that we had integration with compact local oscillators and also some integrated electronics. And then there were a few years that passed while there was sort of what I would say commercialization and really making sure this thing would work in a real world environment. And that was mainly done by the companies involved, in particular Symmetricon. And then finally in 2011, the almost 10 years to the day after the sort of invention of this thing, the commercial CSACs were available. And the DARPA was aiming for this kind of 1 cubic centimeter, 30 milliwatt goal. And in the product ended up being a little bit larger, 16 cubic centimeters and 120 milliwatts. And that really means that that really was because in order to get an output that is useful for people, that is, it's a single frequency with no sidebands on it, and then you sort of have to, the electronics needs to be a little bit more sophisticated than what you would have in a more compact instrument. So just some perspective on this. So back in 1999, when we started working on this, you know, if you looked at the types of clocks that were available, this was basically it. There were hydrogen masers, cesium fountain clocks were just coming online at that moment. You know, vapor cell clocks are on this kind of pink curve here. There were cesium beam clocks, and then there were GPS rubidium clocks. And these are the application spaces, you know, for telecom. This is basically sort of 100 nanoseconds, this dashed line here. And so you could see that, you know, these clocks were, you know, you could hold 100 nanoseconds with a vapor cell clock for about a day. Cesium beam you could do for, you know, years. And this is kind of really what was sort of available. And in the last 20 years, there's been a lot of extra work. Of course, the chip scale clock technology that, of course, is worse than all of these, but runs on a battery. There's this nice clock that came out of JPL, the deep space atomic clock that's based on ions, trapped ions, and microwaves. And this is now, you know, doing really quite well in terms of its performance, although it's a fairly larger thing. But the main development, we also now have commercial fountain clocks and things, but a lot of the main development has been this spectacular progress made using with optical clocks. And now these optical clocks, as I mentioned, are really good. They're basically achieving accuracies in the 10 to the minus 18 range, which you can see is orders of magnitude better than what we had 20 years ago. And this is mainly due to the fact that these optical clocks are based on, you know, oscillators that are much higher frequency. And so we've been also looking at this. So you know, just to give you a sense of what these optical clocks, why they're important, the microwave clocks that I've described until now are based on microwave transitions in atoms, right? So you have a transition that's got a frequency of a few gigahertz. They're usually flipping the spin of an atom. You know, you can get these quality factors of, say, 10 to the 10 for 1 second of interrogation. But of course, you can do this in a different way. You can interrogate atoms based on optical transitions, which basically involve promoting an electron from, you know, its lower lying s orbital out to some higher lying orbital level. And that takes much more energy, 5 orders of magnitude more energy. And so the frequencies are 5 orders of magnitude higher. And because the frequencies are higher, if you can interrogate them for the same amount of time, the quality factors are correspondingly higher. And because this quality factor is higher now, you end up getting better stability because the stability depends on the quality factor of the atom. Now, the caveat on all this is that you can't count this frequency. This is at 10 to the 15 hertz. There's no way of, you know, of counting that. And so directly at least. And so you need to have another piece, and that piece is the optical frequency comb that was developed in the late 1990s and early 2000s. Of course, the 2005 Nobel Prize in Physics was given to Jan Hall and Ted Hensch, basically for the development of this tool. And this allows you to essentially take a laser that's stabilized to an atomic transition with this much higher quality factor and convert it down into the microwave domain when you can actually use it. And so optical clocks are the way of the future, right? I mean, they're now achieving, you know, spectacularly good levels of performance. So we've been trying to work on this also. So we just recently, a year ago, demonstrated a chip scale optical clock. So essentially, instead of having this modulated laser producing or interrogating a microwave transition, we still have a laser, but now we actually directly interrogate an optical transition. And in fact, we use a 2-photon transition in rubidium atoms. So we have this rubidium vapor cell. It's basically the same kind of vapor cell that we use in the chip scale clock, but now we're interrogating the atoms using light. We're collecting blue fluorescence, and using that we can show these kind of quite narrow lines with quite good quality factors. Here's a picture of the cell, and there's this nice picture one of my Matt Humman, one of my staff members, took of this cell with this anti-reflection coating on it here and this nice coffee bean next to it. And now we've been able to integrate this vapor cell with a pair of microresonator frequency combs. So these are very small whispering gallery mode optical resonators, and they can have spectacularly high quality factors of like 1 billion. And so you get massive buildup of optical power in these things. And when the optical power is so high, the nonlinearity of the material, the silica or the silicon nitride, generates this comb of frequencies that can then be used to divide this optical frequency down into the microwave domain. And so here is, you know, so here what we're doing is we're stabilizing a laser onto the atomic transition the optical transition in the atoms. And then we divide that down with this pair of frequency combs, and we generate this 22 gigahertz output. And so here's the CSAC stability in green. Our first demonstration that was published a year ago gave us a factor of 50 improvement. And in fact, our best results now are down a factor of 1,000 improvement over the chip scale clock. And so this looks like a very promising technology for future types of chip scale clocks. I would say that there's still some challenges that remain in getting all this comb system to work reliably. It's basically a photonics platform, and it's a multi-wafer platform, and it's not terribly easy to use, but I think you know, the future's bright. Here are some pictures of these devices. This is the silicon nitride resonator, and here's the silica resonator that are used for these combs. And so, you know, so this is kind of something that we may see in the future. I would say there's still a few years of work to go in terms of getting all this. You know, we demonstrated it all works, but it worked in like 2 different laboratories on 3 optical tables with like 3 racks of electronics. And so we've got to get all that working well to really make this work. But I think it, you know, there certainly is the promise of using these optical standards getting down to very, very high stabilities. So I'll just summarize. You know, I've talked about micro systems, silicon micromachining combined with advanced diode lasers and atomic spectroscopy. And you know, okay, we have microfabricated atomic clocks that will give you 10 to the minus 12 stability over an hour on 120 milliwatts of power and 10 cc's. I didn't mention any of the spin-off stuff, but you can, turns out, using these same techniques, you can make high performance magnetometers, you can make gyroscopes. And the future, at least for timing, I think now is probably in these compact optical clocks. And, you know, I think there's a lot of opportunity for higher performance, but we still got to work out a lot of the sort of technical things about how you get these things to work reliably, especially on the comb side. So with that, I'll just finish. You know, this is kind of an old picture of my research group at NIST, but particularly acknowledge that the staff members, and we've benefited from lots of collaborations with people and great postdocs and students over the years. And, you know, none of this would have been possible without this, you know, team of really, really dedicated people, you know, working hard to make this technology something that works. So with that, I'm happy to take any questions. Thanks for listening.
Wonderful. Thank you very much. So let's start with the questions. Yeah.
I have a question.
Mark, go ahead.
John, the 2-photon clock, I'm trying to wrap my mind around the interrogation technique. Is it like a CPT technique?
It's not. So CPT is usually specific to microwave clocks, right? Because you're basically got these 2 optical fields that you're interrogating the atoms with, and you're essentially trying to drive or excite a microwave transition. This clock is based on direct laser spectroscopy of the atoms. So it doesn't involve, you know, the hyperfine states, the microwave transition at all. It just is it's exciting atoms from their ground state to some excited electronic state, you know, with like an EV of energy above the ground state. And so it's basically just simple optical spectroscopy. We send the laser into the atoms are excited, they then decay and produce optical fluorescence, and we monitor, that's what this signal is here, that we monitor the fluorescence as a function of laser frequency in order to lock the laser up. And so what the standard here is an optical standard. That is, there's no microwave here at all in the optical part, it's just a stable laser. And it's the combs that divide that stable laser down into the microwaves. So all of the sort of atomic stability and performance comes on the optical part, and then the combs are dividing that down into the microwave so that you can actually use it.
So I guess my confusion is around, maybe this, I'm understanding it now, but the excited state that the laser pumps the atom up to must be very unstable, and then the atom decays back down to a ground state?
Yeah, that's right. So if you just, for example, if you just use like the lowest lying levels in atoms, in rubidium, there's a transition at 780 nanometers. And you're exactly right that in the atom, you can excite the atom up there, and then it'll get back down in about 30 nanoseconds. And that leads to a line width that is on the order of a few megahertz. The reason we use this two photon transition, so there's this transition here, you can see goes from this ground state here, there's an intermediate level, and then we excite up to this higher lying 5D 5 half state. And it turns out that this has a much longer lifetime than this state here. And so it's got about 20 times longer lifetime. So now the line width of this two photon transition is on the order of 300 kilohertz compared to like 6 or 7 megahertz that you get on a single photon transition. So the higher the you can excite to, the longer the states are. In fact, if you go, if you excite up to Rydberg levels, which are up near the continuum, basically, those have very long lifetimes. They can be tens of microseconds long. And so that's why we use this two photon transition. Is it's just a narrower transition in the optical domain. And so that gives correspondingly better stability than we would have if we just excited the single photon process.
Thank you.
So maybe another question, John, like, like what are the main things right now, like the remaining things, like basically that are like factors for error in, like, let's say the stability for these clocks, and what do you see like the future, like how we can tackle those things, let's say when it comes to CSAC?
Yeah, so the CSAC technology, so of course the most important region for any atomic clock is at long integration times, right? So you want to time things over hours or days. If you want to have a holdover clock, you're synchronizing using GPS, but then you want to have this reliable, like you want to have in your cards. So the long-term drifts in a chip scale clock are probably a combination of things. One likely culprit is something called a light shift. So let me just go back to the chip scale clock thing. So these chip scale clocks, of course, have light from a laser propagating in them, and that laser light interacts with the atoms and actually causes a very small shift in their frequency.
Oh.
Something called the AC Stark effect, and that shift depends on the amount of optical power that the atoms see. So if the power of this laser drifts even by a small amount over time, that will essentially induce a shift in the atomic resonance frequency, a changing shift in the atomic resonance frequency, and that can cause a long-term drift of the clock. Another thing that can cause a drift of the clock is any kind of change of the gas inside the vapor cell. So if there's any kind of chemical instability where there's some chemical reaction happening that's changing the pressure of the gas inside here, that can cause a drift. The other thing that can cause it is actually helium permeation. So most materials, most glasses at least, are permeable to helium. And so there's 5 ppm of helium in the atmosphere. And so if you have this thing sitting in the atmosphere, helium will slowly leak through the glass into the vapor cell. And even, sort of 5 millitorr of helium is enough to cause a pretty substantial shift. And so there's various things that can, cause this. The drift of these clocks is on the order of, 10 to the minus 9 per year, roughly, is the drift.
So that's an aging thing.
Yeah, it's an aging thing. Yeah, exactly. So it doesn't really show up in the Allen deviation because you have to wait a long time to see it, but that is sort of, I guess it does show up in the Allen deviation at long integration time. So that's probably what what this drift is here, is some combination of light shift and helium permeation, and all vapor cell clocks have this type of drift, right? Yeah. And so it kind of comes down to how, the materials, the glasses you use to make the vapor cell, and how stable your laser can be over like 10 years and stuff like that, right? So it's stuff that's it's a bit hard to deal with. I would say. And it kind of will depend a little bit on how much Symmetricom and Microchip want to invest in terms of getting this down. But it's never going to be super good. But one thing I will say is the optical clock technology, because it's got 5 orders of magnitude higher frequency, it may be much less susceptible to these types of drift things. And so, the goal with the optical clock technology is to get down to 10 to the minus 13 per month drift. And so I think that's, if you really want to have substantially better than what is achieved in the commercial chip scale clock, it's probably going to have to be optical.
Yeah. Okay. Any other question? Like, we are on top of the hour, but let's see, one more question.
I see a question in the chat about this recent tweezer clock project. No, I was not involved in the tweezer clock project.
Okay, great. So thank you for everyone for joining, and we will have the slides and the presentation on the website soon. Thank you, John. Fantastic presentation.
Thanks for the invitation. All right.
John, Elad, anything else you want to add? Okay, wonderful.
Thank you very much, John. That was
Thank
that
you.
was really inspiring. Thank you.
Cheers, John. Thanks very much. Thanks, Ahmed, for setting this up.
Everyone.
Bye, everyone.
Awesome. Thank you.
Bye-bye.
Bye.